We're now going to look at an example that relates a lot of the things we've been talking about. So here's the situation. Does seat location affect grades? Many people believe that students learn better if they sit closer to the front of the classroom. Does sitting closer cause higher achievement, or do better students simply choose to sit in the front? To investigate, an AP Statistics teacher randomly assigned students to seat locations in his classroom for a particular chapter. At the end of the chapter, he recorded the row number, row 1 is closest to the front, and test score for each student. Least squares regression was performed on the data. A scatter plot with the regression line added, a residual plot, and some computer output from the regression are shown below. Notice that if you randomly assign students, then you will know whether it was just the row number that affected their grades, because they don't have any choice in whether or not they're sitting there. So let's look at what happened here. If we were to describe this scatter plot, it shows a fairly weak negative linear trend between row number in which the student sits and their test score. So that would be the way we would describe it. Doesn't seem to have any specific outliers that don't fit in the general pattern of the data. Notice the residual plot is fairly well scattered, so it looks like it's appropriate to do a linear regression. Here's our computer output. We see something here that the R-squared value is very, very low, 4.7%. 100% for R-squared would mean every point is exactly on the line, and we could use row to exactly predict test score. But 4.7%, extremely low. It's probably not a very good predictor of row number is probably not a very good predictor of test score. So let's look at some of the questions here. First of all, what is the equation of the least square regression line? So looking at the data, notice, remember, row number would be our x value. This would be the slope because that's next to x. Constant then would tell us our y-intercept. So we would have test score hat. The predicted test score is 85.706 minus 1.1171 times the row number. So the next thing is interpret the slope of the regression line in context. So remember that slope tells us change in y, test score, per unit change in x, row number. So it says, so we would describe this as saying the linear model predicts, remember that you always need to say that this is a predicted value, a decrease of about 1.1171 points in test score. I'm assuming points, it might be percent in test score, but we'll just say points, for every additional row from the front of the room. So every time you add a row number, then that causes the test score to go down by about 1 point. Not very much. So this doesn't seem to be a very strong predictor at all. Find the correlation. Okay, well, correlation is related to R squared. R is correlation, R squared is, R squared. We could just call it R squared. It's also called the coefficient of determination. So we have the correlation coefficient, the coefficient of determination. So to find R then, all we do is we take the square root of R squared, but we have to remember that it could be either positive or negative. R squared, of course, is always positive, but R could be either positive or negative. So we say R is plus or minus the square root, and you have to put R in decimal form, and you get this number. Now I picked negative. Why do I pick negative? Because this is a downward trend. We see that R would be a negative correlation. If I didn't see the graph, I would know that it was negative because of the negative slope. So if we have negative slope, which we see right here, we would have negative correlation. So that's how you can figure that out, and that is something students forget about sometimes when they're finding R from R squared. So make sure you remember, think about whether it's positive or negative. Is the line an appropriate model? Well, we talked about that. Yes, there's two things. We see a weak negative linear pattern in the scatter plot of the data and no pattern in the residual plot. So yes, we can use that is an appropriate model. Now, that doesn't mean it's necessarily a good model. Does it make good predictions? Probably not. Only 4.7% of the variation in test scores can be explained by the linear relationship with the row number. And the typical amount that the predicted and actual test scores vary is about 10 points. So fairly large if you're thinking of a 100%, 100-point test. So Maybe not huge residuals, but definitely a weak relationship between test scores and row number.